welcome to New Ask Practical Science. I'm Mr Ballaam, and today we're going to be looking at investigating the energy content of food. So this one is quite an exciting practical. We get to use the Bunsen burner, so we do get some fire. And what we're going to be doing, we're going to be looking at the energy content of various different foods. So a few that we are going to look at, we do have a what's it, a Dorito, and also some pasta. So we're going to be looking at these three different food items, and we're going to see which of them has the most energy. So for this practical, we're going to be working through this worksheet. I'll show that one to the camera now for you to look at. We're working through this one, and I'll be following those steps 1 through to 8 to ensure that we get some good results. So step 1, safety. Get those goggles on, make sure our eyes are nice and protected. So now, looking through the different steps on the sheet, we have step 1, and that is to accurately measure out 10 centimetre cubes of water using a measuring cylinder. So what we do, use a measuring cylinder to ensure that the value that we're getting, the volume of water, is precisely correct, rather than just kind of a bit of guesswork and pouring it in. So say we are in science, we do need to be accurate in what we are doing. So what we're going to do, we're going to use the tap here to fill up the water with 10 centimetre cubes of water. So now I've measured out the 10 centimetre cubed of water. Rather than looking at it while I'm holding it up in the air to see if I've got the right measurement, I'm going to put it down on a flat surface, and I'm going to crouch down, and I'm going to have a look at the value so my eye line is level with the water. So with this, we are aiming to get the bottom of the meniscus being on the 10 centimetre cubed mark, which I have nailed that because I'm a top scientist. So the next step, once we've measured out 10 centimetre cubed of water, is to put that into a test tube. So here we have a test tube. So I've just removed a thermometer. Going to pour in that 10 centimetre cubed of water. Make sure that it all gets out there, lovely. And next thing we're going to do is going to use the thermometer. So with that, we're going to take that, drop that into the water, give that a chance to get an accurate measurement of the temperature of that water. So I did use the cold tap, so it may be slightly cooler, but we have to wait and see. Just give that a few seconds to get to temperature. Okay, now we've given that a few seconds to get an accurate measurement of the temperature. Going to check the measurement on that. I've got that as a reading of 19 degrees Celsius. So what we're going to do, you're going to design a table similar to one I've got here, or if you printed it off on the worksheet, that's also fine. So what we're going to do, you're going to have a table that looks something like this. So in the first column, we're going to have the food that we are going to be testing. The next column, we're going to have the initial temperature of the water in degrees C. In the next column, we're going to have the final temperature of the water. So once we've burnt the food, what is the end temperature going to be? Then the final one, a little bit of maths involved, the change in the water temperature. So what is the difference between when it started and when you finished the experiment? So we're going to go through and fill those in, obviously, as we go through the experiment. However, so the first value we had there of the water was 19 degrees Celsius. So we're going to pop that into our table. So because we have degrees Celsius at the top, it means we don't have to write degrees Celsius in every value going down. So with regards to our table, what else can we fill in? So I've told us that the three foods that we are going to be looking at, so we can fill those in. So the first one we're going to look at is the what's it. The second one we'll look at is the Dorito. And the third one we are going to look at is the pasta. So there we go, I've set up the experiment ready to go. We have the Bunsen burner, which I'm going to turn on in a moment so we can set the food alight. We have a heat-proof mat beneath where we're going to be burning the different foods. We've also got the test tube and the thermometer here. Okay, so we've set the equipment up there. As you can see here, we've got the test tube with the thermometer in it, got a nice gap in between the desk surface, which we have a heat-proof mat on as well, just to be safe, and the test tube. So what we're going to do now is we're going to light the Bunsen burner. So I'll first turn the gas on, and there we go. So now the Bunsen burner is lit, I have attached the Whatsit to the end of the needle here. So what I'm going to do, I'm going to set it alight, and then I'm going to place it underneath the test tube with that 10 centimetre cubed of water in, and we're going to see if the temperature changes, and if so, how much. So first step we're going to set it alight using the Bunsen flame. So there we go. So it's caught alight, so now I'm going to hold it underneath the test tube of water here, and we are going to let it burn. So you can see the smoke being formed. So obviously when the fire is burning through here, it's obviously releasing all of that energy that is inside the Whatsit. Obviously you can see that burning still, kind of makes you think twice about eating them. So there we go, so that one's completely burnt out now, so that one's stopped. No, so what we're going to do, we're now going to have to take a reading of the water temperature. So once again, using the thermometer, we're going to look up on what we had here, and we have 37. So I'll just give that another second just to make sure. Does seem to be going up still a bit, so we'll wait a couple more seconds. Okay, it stayed stable there, about 39 degrees Celsius. So we're going to add that onto our table. So we had 19 degrees Celsius to start with. It's now at 39 degrees Celsius. So a bit of quick mental maths there for you. You can see that the change there is 20 degrees Celsius. So somewhat of an increase there. Probably won't have an idea if that's a lot or not a lot, so until we get some comparison figures on the table. So we're going to go through and do those now. Okay, so now that we've got that first result in, the next thing we need to do is we need to swap the water out that we've used to boil. Obviously this is now at a much higher temperature than what it was to start with, so if we were going to reuse that water, it wouldn't be much of a fair test, because we're using the same water again, and obviously it's got that residual heat, so that heat from where we just burnt a Whatsit underneath it, that heat would still be in the water, so that wouldn't be a fair test. So I'm going to change the water that we're going to use, so I'll have to re-measure out another 10 centimetre cubed of fresh water. Here. So once again, we're going to go down to the eye level with the measuring cylinder, so we can accurately get 10 centimetre cubed. There we go, bottom of the meniscus, spot on, well done me. So what we're going to do, we're then going to place that fresh water into the test tube. And so once again, we've got the thermometer in there, ready to record that temperature for us as well. So I'll give that a few seconds to calibrate and get us an accurate reading of the temperature before we set alight to the Dorito. Okay, checking the temperature here of the water. So this one is slightly warmer than what the first one that we had was. So the water to start with on the next value is 20 degrees Celsius. So once again, we're going to burn it, see how much energy gets released from the food. Then we'll have the final temperature, then we'll be able to work out the difference. So have a think to yourself now, which do you think would contain more energy, a Dorito or a Whatsit? So have a prediction. Do you think that it will release more heat, more energy than the Whatsit did, or do you think that the Dorito has less energy? So have a guess and we'll find out in a second. So next, due to the nature of the delicious crunchy Dorito, if you tried to put it onto the needle, it would obviously crack and break. So for this one, we're going to use tongs. So essentially, I'm going to grip them and then do the experiment the exact same way. This just allows, obviously, the whole crisp to be burnt. So going through once again, I'm going to set the crisp alight using the Bunsen flame, and then I'm going to place it under the water, and we're going to measure that temperature change. So let's set the Dorito alight. A bit more alight. There we go. So you can see it gradually setting more and more on fire. Try and get it so it is touching the test tube. Look at that. Oh, a lot of it's fallen off. Still burning there. So this one is burning for a significantly longer time, even though half of it has fallen off already, but this second part here is still alight. So you've got a bit here that is still going, so we'll keep that on. So we'll only stop once the fire has been put out. So, I'm not sure if you can see on the camera, but there are still a few small flames here, so we are going to keep that going. And there we go. So that one completely done as well. Break that off. And then let's have a look at that temperature rise. So once again, give it a few seconds to actually make sure it does get that top temperature. Because if I look at it too early, I might look at it and then within 2 seconds later, it might jump up a few more degrees. So I need to make sure that I'm looking at it when it's at its peak. Okay guys, checking the temperature here now, it's got quite stable and we are looking at 42 degrees Celsius. So 42 degrees Celsius, so we can add that into our table. So as you are looking here now, you've got 20 to 42. So what was the change in the water temperature there? That was awful. That was awful. I was going to let them. So with the 42 there, you can work out that the temperature change here is going to be 42 minus the 20, so you are looking at a 22 degrees Celsius change. So we'll put on here as well that they are both positive, so there has been 22. So if you predicted before that test with a Dorito that it would have more energy, you'd be correct. You can see here, although the two starting values were different, because we're looking at the actual change, those starting values don't matter as much. So clearly here, the Whatsit is on 20 degrees Celsius, change from the initial temperature, whereas the Dorito is 22 degrees higher. So this has 2 degrees Celsius higher, so to release that more energy, just a little bit more. So the next one we're going to test is the pasta. But first, we do need to change the water to ensure that it is a fair test. Okay guys, so once again I've accurately measured out 10 centimetre cubed of water from the tap. So now we're going to place that into the test tube, ready to get its actual temperature using the thermometer. There we go, so once again give that a few seconds to allow the thermometer to react to those changes and give us an accurate reading. Give that a few seconds. As you can see on the camera, should be able to see the mess that we are making here. So this is why we have a heat-proof mat on the bottom to ensure that any of those particles or parts of food that do break off and catch fire obviously don't stain the lovely workbenches. They just go onto the heat-proof mat. Okay guys, we're going to check the temperature now for the final one, and we are looking at 19 degrees Celsius. Okay. So we're going to put that one into the table. So we have 19 degrees Celsius to start with. So all three here have all started at a very similar temperature. However, we shall see how much pasta changes the temperature of the water. So for the final one, we are going to use pasta. So we're going to put this onto the needle, set it alight using the Bunsen burner, and then hold it under the test tube. Okay, with this one, it is burning. There's a very small flame on there that is going. You might not be able to see that on the video. There is a very small flame which has gone out. So with that one, the pasta didn't quite seem to catch fire that well, so you couldn't really see what energy contents it did have inside it. Even so, I will have a look at the temperature on there. So it's slightly increased. However, with this one, so I'll put it onto our diagram anyway, because it was a result that we did get. We did get 23, so there was only a 4 degrees Celsius change there. However, if you do look at the piece of pasta that we have there, a lot of it was not burnt. For some reason that wouldn't quite catch fire. So in this comparison, due to the fact that pasta didn't really work that well, we should probably ignore that value that we have there. Okay, so with that is the practical part of the experiment over. One good thing about you guys not being in, you're not having to smell the awful smell that I'm smelling right now, because burning the food, you may think, oh yeah, barbecues, they smell lovely. Burnt food does not smell good. So following on from this, you should have a series of 5 questions on your worksheet. So I shall show you that worksheet so you know the one. So with that, we've got 5 questions going through there. So hopefully looking at the table for what results that you got, you'll be able to answer some of those questions. So on our one, which one had the highest change in temperatures, which one released the most energy? Obviously looking at the temperature change column here to work that one out. So looking at the food groups that we're looking at here that gives off the most energy, if you're using your knowledge of energy or where we get energy sources from food back in the nutrients lesson that we did, should be thinking on the lines, obviously carbohydrates and fats is where we get our energy from. So obviously looking at the crisps that we had here, obviously crisps got quite a lot of carbohydrates in, so that when they burn, that's why they release so much energy. That's why you get those big flames, so all that energy being released. So obviously with that energy, there's a reason why that we eat the carbohydrate foods, not because we really like crisps and they taste really good. There is an overarching thing of why we do have the carbohydrates in us, because we do need the energy. We need energy for various different things. So one example, obviously just walking around, moving around from place to place. Even going from your bedroom down to the kitchen for your lunchtime snack. Obviously you are using energy. Every step you take, you're flexing your muscles, you're contracting your muscles, you're walking around, you are using energy for those. So another way that your body uses carbohydrates, or uses this energy, is for growth and repair. Obviously, if you think about when you're a really young baby, you start off really, really small, and you've grown all the way up to the size that you are now, I then think by the time that you're a full adult, obviously you would have grown a little bit more as well. So obviously your body needs energy to be able to grow. It needs the energy. That energy comes in the form of carbohydrates that we eat in our diet. So energy is also used for repair in your body. So when you fall over in the playground and you get yourself a cut on the knee or scrape your elbow, obviously your body is damaged and it does need to repair it. But it takes energy to replace those skin cells, to fix the blood vessels that you've damaged. That also uses energy. Another one of the big ways that our body uses energy is to maintain our internal body temperature. Our internal body temperature roughly sits around 37.5 degrees Celsius. Obviously, if you go outside into really, really cold, which it is at the moment, if you weren't able to maintain your internal body temperature, your body temperature would match whatever the environment was around it. So for example, you go outside and it's 0 degrees Celsius, if your body didn't regulate, your body temperature would then stoop down to 0 degrees Celsius and you'd probably die. Likewise, this is similar to what cold-blooded animals do. Obviously, they kind of bask in the sun when it's really, really hot. So you get snakes and lizards, for example, so they absorb all of the heat coming down from the sun to warm up their bodies. Luckily, we don't have to do that. We do it internally. However, we do need an energy source to help us with that. So once you have finished the experiment like we have there, so you go on from this sheet, you'd have drawn a table that looks very similar to my one on the board and put the values in there as well and calculated the change in the water temperatures. So next, on the next sheet along, you should have a series of questions going from questions 1 to 5 for you to answer and have a go at. So with those, looking at those, you're saying, why is the temperature of water increasing? Obviously it's starting at 19, going up to 39, starting at 20, going to 42. So it's going up about 20 degrees Celsius. So why is that happening? So you may sit there and think, well, you've got a fire under it, essentially, you've set the food alight and you've put it underneath it. However, with that, so while you are burning the food, you are transferring that energy that's in the food to the surrounding around it. So in this case, it heated up the surroundings being that test tube with the water in, where we obviously have the thermometer to give us an accurate reading of how much temperature was being given off. Doesn't make sense. So with that, when it was so as we were burning the food, the energy that was being burned from the food was being transferred from the food into the environment, which we had a thermometer ready to actually see that temperature change, so we could gauge how much energy was being given off. So for number 2, you're kind of looking at which one gave off the most, so you're going to be looking at the final column here, so the change in water temperature, so how much did the water temperature change from the start, since after we burned and released that energy in the food, which one had the highest change. So looking at that, thinking for the next question, looking at which chemical food group contains the most energy. So thinking back to your knowledge on a lesson that we did on nutrients, so looking at that, which was the nutrient that we were looking at that we actually use for energy? So we're looking there at carbohydrates and fats. So looking at that, we don't just eat carbohydrates and fats because they taste really nice and you love eating Wotsits and Doritos. We do have a higher purpose really of eating, is obviously to get that energy supply into our body. So there are a few main reasons why we need the energy and the ways that we use it. So one of them being maintaining our internal body temperature. So our internal body temperature is roughly about 37.5 degrees, and that will kind of stay constant because our body controls it to stay that way, a process called homeostasis. However, so that allows our internal body temperature to stay at a pretty constant temperature, even in various different conditions. So for example, if we go outside and it's 0 degrees Celsius outside, our body temperature is not going to match the temperature that's outside. It's going to stay at that same toasty 37.5 to ensure that our body processes and functions can run properly. Another thing that we use energy for is just moving around. A few of you keen sportsmen and sportswomen playing football, rugby, or even just walking around, going from your bedroom down to your kitchen for a snack. Even so, you're still contracting your muscles, you're still walking around, you're still burning energy. So that's another function for energy that we have. Another one being growth and repair. Obviously, when you're born, very small baby, obviously look at the size that you've grown to now in the 10 to 12 years you've been alive, and even then, as you grow on to be an adult, you'll still grow even a bit more. Even with repair, so if you injure your body in some way, it does require energy for your body to repair. So for example, if you fall over, you graze your elbow, it takes energy to replace those skin cells that you have there, and also repair and replace the blood vessels that you've damaged. So quite a few uses of energy. So with that, you're probably thinking, well, do different people need different amounts of energy? The answer would be yes. Obviously, if you have a very, very active lifestyle, for example, if you're a professional athlete of sorts, you'll be training several times a day, you'll be working out in the mornings, afternoons, evenings, you'll be going to the gym, you'll be doing all sorts, you'll be burning loads and loads of energy because you're being really active. So with that, if you're burning loads and loads of energy, you're going to actually need to intake quite a lot of energy as well. So you're going to be eating quite a lot of carbs and fats to make sure that that energy supply is there. Another thing that people often do is the night before a big competition or a big event, they'll have something called like a pasta party. Essentially, they'll carbohydrate load. So the night before, they'll eat loads and loads of carbohydrates. So the next day, when they're doing their football match, their marathon, they'll have loads and loads of energy because they've stored it up from the night before. So compare that to maybe an office worker. Obviously, they get up in the morning, do the normal routine, go to work, and they'll often sit in the same seat for quite a lot of the day while they're on the computer doing their job. So obviously, come the end of the day, 8 hours later, they probably really haven't moved that much. So are they going to have needed as much energy as this professional athlete, or for example, like a manual labour job, so from a building site, are they going to need as much energy as what they would? Probably not. Obviously, they're not not expelling as much energy, so they don't need to intake as much energy. So there is the difference there. What's it called? There we go. Okay, thank you very much for tuning in to investigating the energy content of food. I've been Mr Ballaam. I hope you've enjoyed the practical today, and hope to see you again on New Ask Practical Science.